I'm going to have a quick introduction to consensus models. So, what are consensus models? The whole concept of reaching consensus between different computers started to emerge in the 70s and 80s when people started using distributed systems. So, basically, in the 50s, in the 60s, you had a mainframe. It was very powerful computers that centralized all the processing. And then people started to realize that for really big systems, and if you need to scale, you want to have something that's more elastic, as you say nowadays. So the whole concept of distributing a system, of having a single service being distributed on several computers, started to emerge in the 70s, and it was used mainly to scale up a system. But it's also useful to achieve some kind of redundancy, a system that will be that will be able to withstand failure in a certain site, a data center, perhaps a nuclear war, as some of the early users of the internet were very concerned about. And today it's also used to share custody of systems. So that's the most prominent case we have with blockchains, that multiple parties want to have the system shared between them with no one in complete control. So when we have a distributed system that needs to reach a consensus about the state of the data or the state of a computation, we'd have to handle two types of faults. One, which is almost trivial but not so simple to handle, is crashes. If the system crashes while it has not reached a consensus yet, then we might find ourselves in an incoherent state, where some of the computers in the system know of one state and other computers know of another state, and the system crashed, so now they have partial communications, or some of the servers are offline, and we need to have one coherent state across the system. So that's one fault that we need to handle for. And the other is a Byzantine fault, which I'll tell a little bit more in the next slide. So the whole subject of consensus over distributed systems was researched throughout the 80s and 90s. Two of the most interesting outcomes of this research are the CAP theorem that says that on a distributed system, when you're trying to reach consensus, you can have consistency, which means that every computer on the system knows of the same state. You can have availability or liveness, which means that the system responds and that it's capable of writing and reading data. And you can have partition tolerance, which means that if the network is disconnected, that you'd still have you'd still have the system responding. But the CAP theorem states that you can have any two of these three, but you can't have all three. So that's one thing that limits us when we're trying to reach a good system for distributed consensus. The other interesting theorem that was developed in the 80s is the FLP impossibility. So CAP is very easy to remember. It's consistency, availability, and partition tolerance. FLP stands for Fisher, Lynch, and Pedersen, or something like that. So you can have any two of the three. But basically, what they proved is that if you want to have a synchronous system that reaches consensus, then there's no way you can reach consensus in a finite time. So that sounds very worrying when we're trying to reach consensus across a very distributed system such as a blockchain. But it basically means that we need to have reasonable timeouts above which we can't reach consensus. So we need to have an upper bound on the timing, but we can have absolute timings in which we we are sure to reach a consensus. So throughout this talk, I'll be talking about consensus in an abstract use case of a replicated state machine. So basically, most data systems, distributed data systems that we use are replicated state machines. A replicated state machine means that we share the computation commands between the machines, and that's the way they synchronize the data. So, for example, distributed databases, if you happen to know, they work by sharing a journal, so that the actual commands that are being executed on a database are synchronized between the different nodes on the cluster, and each of them applies it to its local replica. That's in the most distributed architecture. So I promised that I'd say a few words about Byzantine faults. Byzantine faults are the more complicated fault that we have to act with, and that means that unlike a regular crash, in a Byzantine fault we have a node or several nodes in the cluster that are trying to break the consensus. They're evil. So we call them Byzantine nodes. They could be either evil or they were hacked into and somebody evil is controlling them. But it basically means that in a distributed consensus, a Byzantine node might be able to break the consensus by creating false consensus in different partitions of the network. So the example is the Byzantine generals problem. I'll give as an example a very limited example of 3 generals. One of them is a traitor. So this guy is a traitor. And they're on a siege around some city, and they need to decide whether to attack or to retreat. Now they have no chance of surviving if only 2 of them attack. So they need to attack all 3 together or retreat all 3 together. And their only communications is by sending messages via couriers. So they need to reach a consensus. They're voting whether to attack or to retreat. And so the 3, this vote should be easy because it's an odd number. But the traitor does something interesting. He creates false consensus. So the red general wants to attack, and he thinks the traitor wants to also attack. And the blue general wants to retreat, and he thinks the traitor also intends to retreat. So each of the non-traitors thinks that there's a majority for whatever they want to do. And then what's actually going to happen is that the red general is going to attack, the blue general is going to retreat, and the traitor is going to stay and watch. So that's the more complicated fault that consensus protocol needs to handle. So over the 80s and 90s, a lot of algorithms for handling consensus were developed. In the context of blockchain, we'll be talking mostly about 2 types. And unlike what most people think, the 2 major types of consensus that apply to blockchains are not proof of work and proof of stake. They're fast consensus and slow consensus. Or should I say the 2 types of consensus. So fast consensus is the consensus protocol that are usually in use in distributed systems. You know, when you have a distributed database or a file system or something like that, the useful types of consensus are the ones we call fast consensus, or usually in the literature they're called weakly synchronous consensus or final consensus. And these are protocols that reach consensus within a matter of a few seconds. And the consensus is final. So once we know that the consensus is reached, we know that it will not be overturned. So that's very useful for a database, for example. So if a company wants to have a distributed database across some of its servers, maybe some of its data centers, fast consensus is the way to go. The main limitation about fast consensus is that the known protocols for fast consensus need to have a known set of verifiers. And that's not a very easy problem to solve in the context of blockchain. We'll talk about it. Another type of consensus that we can use sometimes for some systems is a slow consensus. So if we relax the requirements of our consensus system and say we don't mind if it doesn't provide us with a consensus immediately and for the consensus to be finite, then we can have an eventual consensus or an asynchronous consensus. And basically the way we do that is that we have turns. We distribute the mandate to sign blocks on our blockchain between the nodes, and we determine which block was in consensus in retrospect. So we might not know in advance or the minute the block was signed whether that block is in consensus. But after a while we will be able to know, because we know that the entire system went behind some node. And the big advantage of such system is that it can be permissionless. We'll describe a couple of protocols that do that, and we'll see how we can be really open with that. So, slow consensus. The most common type of slow consensus that we have today in blockchain systems is a proof of work. So proof of work was initially proposed by Dwork and Naor. And Naor is, as some of you know, he's an Israeli pride. He's a distinguished professor at the Weizmann Institute. And he and Cynthia Dwork developed proof of work in 1993 as a way of combating spam. Basically, the problem of email spam. Everybody can write emails to the whole world because sending emails costs nothing. And the email system is designed not to require any payments for delivery of emails or anything. So it's not very easy to limit the amount of emails somebody is sending. And what they propose is to use a proof of work, so that the person sending the email would have to spend some money on sending the email, otherwise it will not be received. And how you do that is that the content element that you need to prove with your proof of work, you create a puzzle over it. And solving the puzzle is something that you can do with enough computer time. So you have to spend a lot of computer time solving the puzzle, and very little amount of computer time to verify that the solution is valid. So I'll give an example of how it works. In a blockchain, basically, that's basically how Bitcoin works, for example. When we try to close a block, so we construct the block has the hash of the previous block, and it has a list of transactions, and it has a random nonce. And now we say that the difficulty for the proof of work is this number. That's a number in hexadecimal representation, but it's still a number. And any number that has this amount of zeros in the beginning is equal or smaller than that number. So when we say this is the difficulty, we're looking for a block whose hash will be smaller than that number. And we have one degree of freedom in determining that block, and that's the number that we put in the nonce. So we'll start putting random numbers there. So if we put 0, we'll have that hash, and it doesn't begin with the required amount of zeros, so it doesn't solve the puzzle. So we'll try to put 1, and we'll get a totally different number, but it still doesn't begin with the required amount of zeros. So we still haven't solved the puzzle, and we'll keep trying, and we'll try a lot of numbers in the nonce, and after a while somebody finds the number that gives us a hash with that amount of zeros, and that's our winner. That guy just solved the block. Now, he could have put anything in the block. He could have created an invalid block, but if he does that, then the other verifiers are going to know that his block, even though he paid for the computation time and he solved the puzzle, his block is still not valid. So their blocks will not chain to his blocks. So in retrospect, we'll know that although we have a valid proof of work, we had an invalid block, and the consensus does not stand behind it, because the other systems, the other nodes in the blockchain will not follow that block, and the longer chain will be created on other blocks. So that's proof of work, and actually the difficulty level is dynamic. So for example, in Bitcoin, every few blocks, every about a day and a half, the system readjusts the difficulty so that the average block time will be 10 minutes. So if new hardware comes along and hashes are being done faster or whatever happened, and people are able to close more blocks, then the difficulty will readjust and the proof of work will be harder, and we'll find ourselves readjusting and still having the block time of 10 minutes. And that actually creates the cost of the proof of work. So for a given difficulty level, you need to try a certain amount of attempts to solve the puzzle. And as you know, today the Bitcoin system, for example, spends a huge amount of electricity on solving these puzzles. It's about, if I remember correctly, about 0.13% of the world's electricity consumption is spent on the Bitcoin proof of work.
More than Denmark.
Yeah, more than a country.
More than some African countries.
Yeah, more than some European countries.
Really?
Earlier this year, when I was giving this talk, it was more than Slovakia. Now they say more than Denmark. So pretty soon it's going to be more than China.
But it's done in China, so it can be more than China.
That's right. That could be a problem.
You mentioned the parameters for adjusting the difficulty. How can the system do it automatically? How can it know that new hardware comes out?
So it doesn't know that new hardware comes out. It just measures the average time that that blocks were released.
So if it starts to decrease, it increases the difficulty?
Yeah.
That's it? That's the only metric that it uses?
Basically, yeah.
Okay.
So the whole issue of balancing the costs of proof of work with the network worth is non-trivial, because it does make sense that we'd spend a lot of money protecting Bitcoin, because if the proof of work of Bitcoin was very cheap to solve, then anybody would be able to buy I don't know, 10,000 computers and just take over the Bitcoin network. So it has to have some adjustment, that because Bitcoin today is worth about $300 billion, you want it to be hard enough to attack. So it makes sense that we spend a lot of money and a lot of electricity in protecting that. but it is wasteful. Just to give a short recap, Bitcoin and Ethereum are the good examples of the classical proof of work. They both solve the puzzle that the hash of the block with the random nonce is smaller than a certain difficulty level. There are other variants of proof of work. So, for example, Zcash uses a type of hash that is ASIC resistant, so that you're better off solving it on regular CPUs than you are on specialized hardware. So some people think that it's more fair than the Bitcoin and Ethereum proof of work. There are some algorithms for quantum resistant proof of work. So one theory is that when quantum computers are strong enough, that people will be able to use them for solving the Bitcoin proof of work very easily. So we probably have a few years till that comes, but some people are working on quantum resistant proof of work. There have been some attempts to use proof of useful work. One very notable attempt was Primecoin. I think it was in 2015 when they tried to have a currency that's based on a proof of work where you have to find previously unknown prime numbers. That was very nice, but it turned out to be not that useful. So Bitcoin still is dominant.
How about folding proteins? SETI at home.
It's an excellent question. So Ori asks about folding proteins, and there's a lot of interesting computation problems that we do want the world to solve. So why don't we fold proteins or analyze SETI signals, or try to train deep neural networks or stuff like that. But there's a very interesting problem with using that as puzzles, in that you need to assure that whoever proposes the problem doesn't have the answer. So that works very easily with random hashes, but it's pretty hard to achieve with folding proteins, because you don't know if whoever proposed that didn't fold the protein in advance.
Satoshi's, like you said that this proof of work was invented in 93, that was before Satoshi came out with.
Yeah, that was.
Why was the big thing that the Satoshi basically?
Well,
that was already.
It wasn't completely new to Bitcoin. There were a few attempts of introducing virtual gold and virtual currencies that are based on proof of work before Bitcoin. So it wasn't a completely new idea, but Satoshi's introduction did have a very
working implementation.
Yeah, it had the implementation, and it did combine a set of solutions to problems, not only proof of work, that were required to have the first blockchain. So the big novelty about Satoshi's work is integrating a lot of very advanced topics from several
Fields.
Yeah, from several disciplines. Thanks. Okay, so a couple of issues that we want to note when we're talking about proof of work in general is that there's a trade-off between how fast we're trying to close blocks and how likely they are to create forks. So Bitcoin creates a block in average every 10 minutes. If we'll try to tune it to turn the knob and to close blocks every 3 seconds, for example, then what's going to happen is that a lot of Bitcoin nodes around the world are going to close blocks in parallel. and then we're going to have a lot of forks, and it's going to take us longer to reach the eventual consensus. And some work is done on solving that, such as Spectre, for example, which adopts forks as a way of life. Another big issue with the proof of work is that it does create a very high carbon footprint, and I think speaking of consensus, there's a wide consensus that global warming is a problem, and creating a payment system that creates such a high carbon footprint is a problem. So here's a suggestion. Instead of having somebody pay in petrol dollars to solve the proof of work puzzles, why don't they pay with virtual money? Or just prove that they have it. So here's proof of stake. Proof of stake says we'll give you the mandate to close a block in random that is weighted on how much of our currency you have, and maybe people will be able to vote on your on whether your block is valid, and we'll use that instead of the proof of work. So it's just as good for being open, so that we don't need to know who you are. You can, as long as you can prove that you have our currency, our token, then you can have the right to close blocks. So it's open, it's permissionless. There's several protocols for doing proof of stake. There's a lot of complexities about actually implementing it, because you need the token holders to be online and to be able to vote on the validity of blocks. So that's a very complicated issue to resolve in real life. So some system, for example, Ethereum is planning to adopt a protocol that uses bonding, that requires whoever wants to participate as a verifier to put its tokens in a security deposit, and they're only going to get it after a while, so they can't use their money while they're using it for voting. There's some systems that also apply some game theoretical incentives for creating valid blocks, so that your money could be confiscated if you create an invalid block or stuff like that. When we're talking about the disadvantages of proof of stake, there's a lot of complexities in its implementation and in getting it to work on the real world. But aside from the practical challenges, there's also two very problematic theoretical or philosophical challenges. One is called the nothing at stake problem, and that means that unlike proof of work, where the person closing the block has paid a lot for closing it, so it's not worth it for them to risk creating an invalid block and not have the consensus behind their block. With proof of stake, it's almost free to close a block once it's your turn. So why not create several blocks? Why not create a Byzantine attack or a double spend or whatever? So that's called the nothing at stake problem. Another more philosophical problem is the circular logic problem. Basically, we have a virtual currency. We have the ledger that decides who owns that currency, and the ownership of that currency is used to vote on the consensus of who owns the currency. So there's a problem there, if you notice. Being very abstract and very philosophical, there's a lot of researchers in this subject have different approaches to this problem, or whether it exists at all. I'm not going to get into that. Just as
I have a question about the first challenge that you mentioned.
yeah.
About the nothing at stake. Isn't the like if a leading stakeholder tampers with the ledger in favor of himself, isn't he devaluing his own assets eventually? So this acts as an incentive to not do it.
So that's a good question.
It breaks his own system.
Or he's saying if somebody who owns a lot of currency, a lot of stake, and has the voting power thanks to that stake, if he attacks the system, then he's undermining the value, the intrinsic value of the currency that he has. So it damages his own property. So that's true to some extent, but the same would be true with you could say for majority stockholders in public companies, but they're still capable in some circumstances to make business decisions that are better for them than they are for the minority shareholders. So sometimes, I mean, if you try to steal the entire world supply of Bitcoin, then it would make Bitcoin worthless. You wouldn't be able to do anything with the remaining Bitcoin. But if you'd steal just a little bit, then you might get away with it. So examples of public blockchains that are using proof of stake as a replacement to proof of work. One very prominent example would be Ethereum, which I also mentioned as a system that's using proof of work, but Ethereum is planned to start moving towards proof of stake with Casper, and that's expected towards, it's going to be gradual over the course of several years, but within 2 or 3 years we're supposed to see it in production. Another example is Cardano, which has become very dominant very fast. I think many of us haven't heard of Cardano a couple of months ago, and today I think they're the number 5 biggest blockchain by market cap. So I don't know if they're going to remain there in a month, but they're going up very fast at the moment. So they're also using proof of stake as a replacement to proof of work, and they're an open system that's very interesting. Now about fast consensus protocols. I've already mentioned that fast consensus protocols are very useful in distributed systems when we don't need to have an open system. If we just want to have distribute our database over several data centers or over several servers, that makes a lot of sense to use the fast consensus protocols. Over the years, a lot of protocols were developed. You may hear of some of them. The variants of Paxos are very common in distributed systems. Also, some of the derivatives are common in blockchain technology. PBFT, the Practical Byzantine Fault Tolerant protocol. It's a very simple protocol that is Byzantine fault tolerant, as its name implies. It's very easy to implement, very fast. And a lot of newer implementations that we hear, since there's a lot of activity around the blockchain technologies. We see a lot of developments. One example will be the BA star, which is Byzantine agreement protocol that's designed especially for a blockchain system. So it's designed for AlgoRand, which I think I'll mention in one of the next slides. But basically, with all the fast consensus protocols, the requirement is to have a known set of verifiers. And preferably, that should be a small set of verifiers, because it's much faster and safer to reach a consensus on a set of 20 verifiers than it is on a set of 20,000 verifiers. So that's the big challenge of creating a fast consensus in a decentralized system, especially if we want it to be open. But the trivial solution is to have it closed. So let's have a private blockchain. So of course, a private blockchain is not useful for all the cases where somebody might want to have an open and public blockchain. But if we want to have a blockchain that's internal to our company, then we can just install a set of servers and use one of the very fast consensus algorithm between our blockchain servers. That's very easy because we control everything. We can decide who's the nodes. We trust the nodes. The nodes trust each other. So everything is under control. We can also use the same method by several companies if they form a consortium. So that might not exactly be decentralized, but it's useful in some contexts. So one very interesting example of using that is for example, for a company to share the blockchain that manages a certain project with its customer, so that neither side has complete control of that database or that ledger, and because they have shared control over it, then each one can trust that its contents were not manipulated. So an example for private blockchain technology that's very common today is Hyperledger, which is developed by IBM and the Apache Foundation. A lot of enterprises are starting to use that internally for their internal blockchain needs, whatever these are. Another way of approaching this problem is to form a federation. So basically what you say when you form a federation is that we don't want to have a consortium because that could be seen as a central solution. So let's have a network where everybody is independent of the others and everybody can make their own choices. But everybody communicates with one another, and where I accept the verification of a few of my peers, and my peers also accept the verification of the same peers and myself, then we have some consensus about who can approve a consensus. And we've done that without creating any central body that owns the consensus. So that's a decentralized solution. It does allow us to have a small and known in advance set of verifiers. So that allows us to use the very fast consensus protocols. It does require us to modify the consensus algorithms a little bit because we need to have the ability to have our consensus sets partially overlapping. Obviously that's possible because we don't have any central body that's coordinating us. But that works. Ripple are using this method. Ripple also quite big. Today I think they've reached $80 billion. The number two, they're bigger than Ethereum by market cap. That's a bit surprising, but it's very impressive nonetheless. Also Stellar are using that. That's a very interesting practical solution to having a decentralized fast consensus algorithm. Another family of fast consensus algorithm is delegated proof of stake, and that basically means we'll take the concept of proof of stake, but because we want to have a very limited set of verifiers and we want them to give good quality of service to the blockchain. We want them to be online and to have fast servers and fast connectivity. Then we'll delegate the work. So I can say that I have, for example, a certain amount of a token. So I can appoint a certain delegate to do the voting for me. So that works pretty much like parliamentary democracy. So like a citizen would elect his Congress member or Senate member. In that case, might be a more appropriate example. And they do the voting for them. Very much like parliamentary democracy, there's the risk of the delegates not acting by the interest of the voters. So delegates could be corrupt, and there could be a problem of voter indifference. So a lot of times the voters wouldn't care too much about what their delegates are voting in their name. So that creates a problem. And of course, the other proof-of-stake problems still apply. But a lot of very prominent blockchain solutions are using this system. BitShares, I've been using it for a couple of years. Steam, which launched earlier this year, is basically a fork of BitShares. They're using, both of them use, I think, 101 delegates. Waves also running in production using delegate proof of stake. And EOS, which launched their testnet and are expected to launch throughout 2018, a very high performance network, and also using delegated proof of stake. And last but not least, another example for a fast consensus algorithm, that's AlgoRand. That's a very interesting model. It's still not used in production. A lot of practical issues in creating a production network that uses it. But the very interesting idea, the idea of cryptographic sortition. What AlgoRand introduces is that every person in the network, every user could be a verifier based on some weighted turn taking.
You mean is it every full node, or like also
everybody? That's one of the answers of the issues, whether everybody needs to be a full node or people need to only synchronize the network when it's their turn to vote. And it's still not that easy, even if you know when you're about to vote and you only synchronize then. But basically how it works is that before the block time and only when the block time arrives, you can know if you're in the very limited committee that votes on the block. And nobody else knows that in advance. Nobody else can know whether you're in the committee or not until you've already done your proof. So it's impossible to attack you in advance, knowing that you're going to be the voter. So that's a very interesting model. Still needs some work before we can see if it can be used in practice. And I guess that's it.